So Manoj has been with us at UEA for about a decade, I think, and we've been trying to keep him down on Earth, but every now and then he seems to wander off out of the solar system, including today, I think.
Right. Thanks, everyone. So, yes, so we're usually used to dealing with the climate of Earth, but this particular talk is going to be something that maybe some of you haven't really seen very much of before. And this is the climates of terrestrial planets orbiting red dwarf or M stars. So it's a stellar classification type thing. An M star is a small dim star. It's otherwise called a red dwarf or a red star or something like that. And it turns out that the climates of these planets are actually quite interesting and very different to what you might expect to a planet like Earth. And there are reasons for looking at planets like this. So I'll be talking about just the zoo of exoplanets we have now, things called habitable zones or Goldilocks zones that you may have heard of, and I'll concentrate finally on planets orbiting M stars. So since 1995, this is the first discovery of very large exoplanets by Mayer and Coloz and others. 5,098 planets are now confirmed discovered. This is confirmed discovered orbiting other stars that are light years away. I mean, I think this is extraordinary. It's almost science fiction. That number's actually wrong. I wrote this talk last Wednesday. I looked it up at lunchtime, and it's now 5,106. 61 in the last decade of the 20th century, over 500 in the first decade of the century, 350 in the last 2 years. A lot of very busy astronomers during lockdown there, I think. But these planets are being discovered at an exponentially increasing rate as techniques are honed, as instrumentation improves, as technology improves, etc. So of these, 950 confirmed have masses less than our solar system planet Jupiter, and 40 confirmed have mass radius of the Earth or less. It must be remembered that this isn't going to represent what the actual distribution of planets orbiting these stars actually look like. These are essentially the limits of the technology that we have. We can see very large objects orbiting very small stars. It's very, very hard for us to see Earth-like objects orbiting Sun-like stars. So there's a massive selection effect going on here. But having said that, the fact that we can still observe these things, I still think is incredible. And of course, there's a huge interest in any of them supporting life, which is not really what I'm going to talk about, but it is one of the things that motivates these things philosophically. So one of the things that motivates these things is something called a habitable zone. And this is a concept that was brought about by an astronomer 60-odd years ago. And it's a locus of orbits around a star around which liquid water is stable at the surface. And the reason for that is everywhere where there's life on Earth, there is liquid water. I mean, it may be acidic, alkaline, it may be hot, cold, huge pressure, because Lord knows what dissolved in it, but it tends to be liquid. And it's used as a sort of imperfect proxy for the presence of life, and it does motivate a lot of study, but certainly not all research. Astronomical, planetary science research isn't really motivated by these sorts of questions, but they are questions that people are interested in, because everywhere where you see liquid water on Earth, you do have life. But the habitable zone can also tell us about potential planetary types. We don't need to look at this as a biological type imperative, but we can think of it as a very useful climatic indicator. It can tell us about potential climate types such as Venus, which has lost its water and has got a CO2 super greenhouse. Earth, we know a lot about. Mars, which unfortunately seems to have lost most of its atmosphere and is now a cold desert. Europa, which is essentially a shell of water, well, essentially a moon of Jupiter, which is water encased by a shell of ice, and it's just tidal friction of its orbits around Jupiter, its interaction with Jupiter's moons, keep that ocean liquid. And Titan, which has lakes, clouds, and precipitation, but those lakes, clouds, and precipitation are all methane rather than water, because it's so far away from the sun that methane is stable in large quantities there. So there's a very large variety of atmospheres just in our own solar system, and these have been studied extensively for the last half century or more. But what does a habitable zone mean for an M star? And this is a really famous plot in the planetary sciences field. Vertical axis, the y-axis, Dave's confusing me now. The y-axis or the vertical axis is stellar type. So the sun is a G star and it's round about there at 1. An M star is having a stellar mass of 0.1 to 0.5 solar masses. So it's a 10% to 50% of the mass of the sun. The distance is in AU. So this is astronomical units. 1 astronomical unit is the distance from the Earth to the sun. So you can see the planets of the solar system are represented there: Mercury, Venus, Earth, Mars, Jupiter, Saturn, and out to Pluto. The habitable zone is that yellow stripe, and it's essentially pretty much giving you contours of stellar flux. And you can see it's a very strong function of star size that I'll come to in a second. The inner edge of the habitable zone, this is where we think that we tend to get Venus-type planets. This is set by what people used to think was the runaway greenhouse effect. This is done over 50 years ago. Essentially, you get so much stellar radiation hitting the planet that the ocean simply boils away. It gets that hot. You get a runaway greenhouse, essentially. The atmosphere is made up out of various windows in the infrared, and those windows essentially shut as the concentration of water vapor gets higher and higher, and the temperature of the planet can just run away. But actually, about 30, 40 years ago, other theories came along that actually said, well, Venus potentially is more like a situation where you warm up the planet enough that the middle atmosphere and upper atmosphere warm up enough that hydrogen starts being lost from the planet's atmosphere. These gases are being lost from planets' atmospheres all the time, from Earth, from Mars. But if you can increase the concentration of water or hydrogen in the upper atmosphere of your planet by orders of magnitude, the loss rates are such that you can lose an atmosphere over a few millions or tens of millions of years, which geologically is not that long. And once you lose all your water, you're studying CO2 pumped out into the atmosphere through volcanism, and there's no weathering to take that away. So that's one of the theories as to why Venus is how it is. The outer edge of the habitable zone is simply the planet is too cold to support carbon dioxide. It all condenses out. It may form clouds and condense out, but eventually it forms into CO2 ice. And indeed, the planet Mars, its polar caps are they vary seasonally, but sometimes they're pure water ice, sometimes they're frozen CO2. And you can actually see that in surface pressure cycles of the Martian atmosphere. But what's interesting is this sort of tidal lock radius. If an object orbits too close to another object, over time, tidal stresses will bring that smaller object into synchronous rotation. In other words, one side of this smaller object will always face the larger object. So the moon is synchronously rotating the Earth. The Earth isn't synchronously locked to the moon, but the moon is to the Earth. And if you look at where that dotted line is, unfortunately for M stars, it's actually way outside the habitable zone. So any planet that actually orbits an M star or a red star could well be tidally locked to its star if it's in this habitable zone in which you can support liquid water. But it should be noted, of course, this is just looking at specific types of terrestrial planets, like Europa, which orbits Jupiter, Titan, which orbits Saturn, and Venus lie outside our habitable zone. And there's plenty of really interesting atmospheric dynamics done about those 3 planets. And people have also suggested the presence of hydrogen atmospheres way far out in stellar systems in which you have a very, very cold planet with a very dense hydrogen atmosphere which can actually support a very strong greenhouse effect and keep the surface of the planet warm. So why are we actually interested in looking at these dim red stars? Well, these dim red stars actually form 4 out of 5 main sequence stars. So main sequence stars are those that live a long time. So there's a lot of them. There's far more M stars than there are G stars or yellow stars. And because this luminosity is a strong nonlinear function of mass, as I said, the habitable zone, it's very close to its star and within the tidal locking limit. So one side of the planet always faces the star. Only one side is ever illuminated. So prevailing view was that, well, one side faces its star, one side never faces its star, one side would essentially be boiling hot, and the other side, the gases are just going to be cold enough to condense out, and you might actually get atmospheric collapse, or at the very least, your hydrological cycle will ensure you just get a huge polar ice cap and there's nothing going on in the atmosphere. This actually is thought to happen periodically to the Martian atmosphere, which actually gets Milankovitch cycles a bit like Earth, but they're much, much bigger because Mars is no big moon. But that's been theorized. But what's the situation really going to be like? Because we know that atmospheres and oceans transport heat. They transport huge amounts of heat. So is this situation really warranted? So we decided to look at this using an atmospheric model. So how do you construct a simple global circulation model of a theoretical planet when half your mates are laughing at you? You keep it simple. I mean, okay, we had to keep it simple because of computational requirements, but actually I'll show you the models that are being constructed now don't have to be simple because we have planets to actually try and infer things from. So what we did was we keep the planet as the same radius as Earth. And this is sort of implicitly done already. We're sort of asking the question, if Earth was moved and simplified to a ball-bearing planet and put around an M star, what would it look like? There's also lots of reasons for looking at planets that are similar radius to Earth. If a planet's much smaller than Earth, it's more likely that it's going to lose its atmosphere like Mars did. If a planet's a lot bigger than Earth, it's more likely it's going to form some sort of sub-Neptune type thing with a very, very deep ocean of kilometers or tens of kilometers deep, which is interesting in its own right, but we don't really understand how atmospheres would work in a thing like that. We have a very simple pure atmosphere, pure CO2 atmosphere. But one thing we can do, because of synchronous rotation, is we know that the tidal locking means the rotation period is the year length. If you know how far away a planet is from its star, you know the mass of the star through Kepler's laws, you can work out things like the year length. So you can know things like the year length and the distance away from its star. And if a planet is synchronously rotating around its star, it means that the year length is the same as the rotation period. And this is very, very important because, as you know, rotation is very, very important for both atmospheric and ocean dynamics. So for these sorts of planets orbiting these sorts of stars, we can actually say something about the rotation period that we couldn't actually say for a planet orbiting a yellow star. We then had some very simple constructions for like energy balance and radiation. And then, because the model's simple, this is the old Reading SGCM with a grade radiation scheme from my boss at NASA Ames. And this is what we got. This is essentially, this is showing a cross-section of temperature, but rather looking at a zonal cross-section as we used to, this is actually going around the equator of the planet, from the dark side of the planet to the sunlit side at 0, and to a longitude away from the substellar point of 180 degrees. That's dark, starlit, dark, and it's temperature on the vertical axis. And the three different runs are three different surface pressures. And what we found is for a sort of quite simple setup, you actually don't need a very high surface pressure, something like Earth, and you don't get atmospheric collapse or anything like it. Indeed, for a surface pressure of 1.5 atmospheres, the dark side's actually warmer than the freezing point of water. And this is actually quite interesting because it shouldn't be a surprise that atmosphere and oceans transport a huge amount of heat. Indeed, when I did this paper, astronomers were like, well, it's a climate model, we're not sure. Whereas a colleague from Reading Meteorology went, you got a paper out by showing that atmospheres transport heat, seriously. So I guess, it may be obvious or not obvious, depending on what your field is. I mean, here you've actually got a planetary atmosphere transporting heat in the direction of its rotation, so it should be very, very efficient. So the fact that you actually really do smear out temperature gradients with the atmospheric dynamics shouldn't be a surprise. What is interesting is the cross-sections now looking versus latitude. The top plot actually shows the zonal winds on this model, and what we get is a very strong so-called superrotation. What we get are westerly winds at most latitudes, including the equator, and these are essentially being forced by atmospheric waves in the model, which are themselves forced by this very strong east-west-east temperature contrast that essentially forces atmospheric waves, that gives you these very strong westerly winds. The zonal cross-section of temperature is also interesting. It sort of looks like what you might expect from Earth, but at the very bottom you can see there are these very, very strong inversions. And the atmospheric temperature cross shows these inversions are actually associated with very, very strong temperature inversions on the dark side of this model planet. So loads of work has now been done since then on these sorts of planets. We included water vapor and clouds in what's now known as the IGCM model, is the IGCM3. People have looked at cloud feedbacks and what that does to the width of the habitable zone. People have looked at the effective rotation rate and what that does to the atmospheric dynamics. And people have even looking at convection resolving modeling of the daylit side to see whether actually that changes when you've got resolved as opposed to parameterized convection. And people are now including the oceans. Now, when you look at the oceans of a theoretical planet, you have to be very careful. We have no idea of continents. We have no idea of barriers. So should you have a barrier or not? What sort of continental distribution do you put in? Do you keep it simple? So these sorts of things are the sorts of things that are going to be affecting how you represent oceans in these planets. But there are papers that have looked at ocean heat transport and also effects of rotation rate. And there's Jodie Cullum, who did a PhD thesis here with Dave Stevens and myself a few years back. Another interesting thing about M-stars is something that you don't really think about on Earth, is that if you think about the spectral variation of ice and snow albedo, its effects are actually very different for a planet orbiting an M-star than for a planet orbiting a yellow star. The top plot shows the different spectra. The black line is an approximation of what you might get for the Earth, for the Sun, and the red and orange lines are actual spectra of actual observed M-stars. You can see because they're colder, they're dimmer, they peak at about a micron, not half a micron like the Sun does. But these are the wavelengths at which the albedo of ice and snow actually decrease from very high values to very low values, which means that essentially ice and snow albedo feedbacks are much, much weaker on planets orbiting these stars. And runaway glaciations are much less likely in that paper by Shields et al. I'm really proud of this paper because that was 15 lines of IDL code, which then became 25 after review number 2. Okay, right. So other examples of recent research, climate models are now being used to simulate climates of actual planets. These are actual planets that have been found, Proxima b and TRAPPIST-1 BCD. There are even climate model intercomparisons of these planets. We know the approximate size of the planets, and you know how much stellar radiation they get. Of course, you have to make assumptions about their makeup, so you can run with 2 or 3 different assumptions of the atmosphere. And all important is to create synthetic spectra. You fly spacecraft through the model in order to create spectra that you compare with observations. But wait a minute, before I finish, you may say, this is a meeting about CRU. Where is the data? You're just making up planets and stuff. Well, atmospheric collapse on synchronously rotating planets depends on these low-level inversions. How can we estimate how large they might be? Which is absolutely, dependent on what our models are doing. Well, actually, we can use data from Antarctica during polar night, which is a good approximation, as good as we can think of, to actually see how deep these atmospheric inversions may get and what they may tell us about potential atmospheric collapse. So the first 3D climate model of these planets orbiting M-stars was run over 25 years ago, and there's now a zoo of exoplanets and a whole bunch of climate models to compare it with. These things still feel like science fiction to me. I tell my students here it's incredible what they can do now, and the rate of these discoveries is increasing exponentially. There's more detailed data emerging. There's the James Webb Space Telescope, which will be returning soon. The astronomers reckon we'll be getting outgoing long-wave radiation type data from terrestrial-size exoplanets in the next 10 years, perhaps, maybe sooner. So maybe this will show how Joshi et al. 1997 and the subsequent papers weren't actually science fiction after all. Well, I don't know, hopefully. Who knows? But we'll see. That's it. Thanks for your attention.
Great, thank you, Manoj. Any questions? In the room first again. I have one, but I'd rather go to the audience. Okay, I'll ask mine.
Don't believe a word of it.
You mentioned that smaller stars are smaller planets are more likely to lose their atmospheres. Why is that?
Smaller planets,
Putting you on
this now. So with smaller planets, in the case of Mars, its magnetic field just isn't strong enough to hold the atmosphere. So the magnetic field can essentially stop the solar wind or the stellar wind from stripping away the atmosphere. For Earth, you have a strong magnetic field that protects it. For Mars, you don't. For Venus, the rotation rate, it's almost the same size as Earth, but the rotation rate is different, and people aren't really sure what happened there. So it's planetary size and magnetic field and what's happening in the core, really.
Okay, thank you. Michael, are there any questions online at all?
No, they're very shy today.
Okay. I have a question. Should we go to Amanda first? Oh, there's a room mic coming to you.
So you said that obviously what we know about exoplanets is very much constrained by our observational capabilities and how that's changed over time. Are there any new telescopes or things in the offing in the next 5 to 10 years that are likely to revolutionize that observational capability in a big way?
Oh, good question. There are loads of things planned, but very few of them come to fruition. So the James Webb is, I think, the one people are really looking for. And the exoplanet, people have really taken over a lot of its science priorities. So that will be returning data over the next, hopefully, year or two. We'll start sending about interesting things. There are missions planned, such as huge interferometers in space to give you a big baseline and look at these things, but they cost a lot of money. And so it's very difficult to get them built. But you can do a lot with present-day technology. If you use the new technology to basically point at something, you can then use the present-day technology once you know where to look and start characterizing things a little bit better. So use a combination of what's new and what's older as well. I don't know what the latest is in terms of stuff that may get launched in 5 years and is likely to be.
Thank you.
Edward, I think, had a question. If you can keep it fairly, or at least keep the answer fairly brief.
Yeah, thanks for that excellent talk, Manoj. I was just wondering about how big the global community is looking at climates of exoplanets.
Let's see. So there's a meeting in 2019 in the before times in Oxford, which is this community, and it was about maybe 2/3 of the people in this room. But the community of people looking at the solar system is big because that's half a century old. But it's interesting, a lot of people who do atmospheric science tend to look at terrestrial planets. A lot of people doing ocean science tend to look at giant planets, and that's essentially the Rossby radius compared to the size of the planet determines that, so that's quite interesting.
Great. Okay, thank you for that. I think we should thank all three of our speakers from this excellent session. So thank you for joining us. Thank you for joining us online as well.